All right, we are officially starting the
Online.
program.
Oh,
We are
official.
online and ready to rock. And we've been
All right.
having a highly intellectual conversation about
Yes.
being able to own a kangaroo without a permit. If you want to own a kangaroo without a permit, you must live in either South Carolina, West Virginia, or Wisconsin. You don't learn this kind of stuff anywhere else, people. I
That's
want you
right.
to know this. TACO goes the extra mile to give you all of your kangaroo related information. Just the way we are. We're those kind of
Yeah.
guys, right? We're those kind
There's
of guys. So if
so
you
much
live in the
information.
states of South Carolina, West Virginia, or Wisconsin, you may own a kangaroo without a permit. Several other states require a permit, and then a bunch of states, the killjoy states, say no kangaroo, no way, no how.
So we have our resident kangaroo online tonight too with us.
We do?
Yes, Joey
Ah.
Inglema. Yes,
Oh, Joey. There you go.
Joey. That's the baby kangaroos, right? So
Joey,
he's here.
that's right. He's
Yeah.
he's a baby kangaroo. That's right. That's right. That's right. And how does one obtain a kangaroo permit? Well, you have to go to kangaroo court. I just came to me. I kill me. I kill me. Good God. All right, let's get to work. Good to see
Oh,
you
boy.
guys again. Glad you guys are here with us. Let's get the show on the road and save our souls.
That's it.
First
That's
thing
it.
first, tonight is a politics-free zone. There's no politics tonight. We're talking hydronics and variable speed pumps. So politics-free zone. Check it at the door, peoples. All right. And I want to welcome everybody to episode 6 of TACO After Dark, the fall edition. All right, the fall edition. And tonight's topic, we're going to start to talk about variable speed pumps. This is going to be a two-parter. This week and next week, we're going to talk about variable speed circulators. But tonight, we're going to really do some myth busting, because what we have learned, all three of us have learned in our travels, and is that people know they vary their speed, but that's kind of about it. And the misinformation out there has just gone way overboard. And most people think they're kind of like magic. You push it in, you stick it in, you press a button, and it just figures everything out for you. And that's not necessarily the case. You need to know a lot about these things, because the more you know about them, the better you can apply them and use them to their peak benefit, which is enhancing the overall performance, efficiency, and economy of operation of the system. That's the goal of using a variable speed pump. So we're going to discuss some of those myths and some of those, outright untruths, and give you some basic background on what they do and how they do it. And then next week we'll get into some of the different types and the applications and where they work best. So Dave, Rick, anything more you guys would like to add to that, or give our gang a welcome here?
Go ahead, Dave.
Oh, okay. Yeah, welcome everybody.
Catch you guys off guard.
I know I'm taking care of the tech stuff behind here. Also one of the things to remember about any of the variable speed pumps, and even the ones that we'll show you today, don't be afraid of them, because you're not going to get serial number 001. Okay, they've been around a long time. We've been making them here at TACO already 8 years. TACO Italia has been making them for almost 20 years now. So don't be afraid to try them. They've got track record behind them. We wouldn't have them if they didn't have any good track record.
Yeah.
And in fact, TACO Italia actually introduced the very first ECM variable speed circulator in the world back in 1999, 2000. So again, we have the technology we have the background with a lot of experience and a lot of technology there. So again, as Dave said, don't be afraid of them.
Yeah.
All right.
Yeah.
Well,
go ahead.
Rick.
Well, just
No,
as
go
far
ahead.
as modes of operation, there's some simple little rules of thumb you can get into to, if it is midnight and, you got no time to do the math, as we always teach you. There's just some simple little subtleties that you can use depending on how the system's piped to know what mode to get it in. And the mode very important part of getting circulator applied. You know, you pull these things out of the box, they got all kinds of things they'll do. We're going to get into a little bit of that tonight. John specifically talking about this, you know, this magic thing that supposedly does everything. So anyway, modes of operation, and there's some easy things to remember, and I think you'll get quite a bit out of that. So.
All right. I'm not sure if that's on my end or not, but if you guys heard Rick, okay. That might be internet connection on my end. I'm not sure.
Heard
Well,
him just fine.
Oh, okay. Sure. All right, then that must be on my end. So let us go. Tonight's cast of characters. Tonight's movie is, of course, The Princess Bride. We did joke earlier that it was the Dave Holdorf story, but it really isn't. Okay, it really isn't. And tonight's cast of characters, of course, led by my favorite character. Since I'd made the presentation, I get to be Inigo Montoya. And then we have Dave and then Rick as Fezzik. So there's your cast of characters right there. And why The Princess Bride? What's with the shirt? What's that name tag say? Well, here's the name tag. I bought this t-shirt. It has a little name tag on it. It says, "Hello, my name is Inigo Montoya. You killed my father. Prepare to die." I love that line. I love that line.
Inconceivable.
Inconceivable, right? Last week we had a good time. We talked about circulators versus zone valves, and we had hopefully we gave you some information there that'll be useful. We talked about the inner workings of the 571 heat motor zone valve and then the Taco Zone Sentry zone valve, and gave you a little demo on that. And we went over some wiring schematics to kind of help you understand how to make use of the zone valves and our zone valve controls, where you could actually run up to 3 circulators on one zone valve control. So that was all last week. This week, we're going to get into, as we said, ECM myth busting, and also what happens in a zone valve system, what happens within the system when zone valves close. That's good stuff. What happens when zone valves close, and what kind of dynamics take place within the system. Last week, we did mention that, you know, flat curve pumps and zone valves go together like cake and ice cream, whereas steep curve pumps and zone valves go together like tuna fish and ice cream. We're going to explain why that is tonight. All righty, so let's get this party started once again. See, we're all friends here, right? Look at that. Look at that trio. What a group. You wouldn't know that those 3 guys can run, are like hydronics training guys, right? Or maybe you would, I don't know. So let's talk about.
I heard Andre the Giant was so into hydronics way back then.
He was.
Yeah.
That's why he was a big, pardon the pun, hydronics fan. So why use variable speed circulators? That's a pretty good question. Why do we use variable speed circulators, and what do they do? It's funny. One of the biggest things I get from people is when I ask them that, I go, well, it's efficiency. Okay, what kind of efficiency? Electrical efficiency. Okay. Well, how much electricity does one of these things save? Oh, a buttload. Okay, how big of a butt? I mean, it's when you look at it, and we can actually do this mathematically, we can actually quantify how big of a butt this is, how big of a butt we're talking about when we talk about buttloads. We can say the bigger the circulator, the more electricity is saved or not consumed. The smaller the circulator, the percentages are great, but a calculator might tell you a little bit of a different story. But somewhere along the line, we were convinced that, oh, we got to use these things. They're going to save an incredible amount of energy for our customers. We'll quantify that. We will most definitely quantify that. All right. Some myths that we hear, and again, a lot of stuff that gets repeated out there, even amongst people who sell these things. You hear them and you shake your heads. They save energy. Well, yes, they save electricity. They are more electrically efficient. That is one thing that they do. Do they do other things? Well, again, it depends. We've heard people say that they always give me the right flow. I use variable speed circulators because they always give me the right flow. That phrase, my friends, is about 83% correct. Its accuracy level is about 83%. It needs 2 more words to be 100% correct. And those 2 words are hardly ever. Okay. They always give me the right flow, hardly ever. Hardly ever. Just because something varies its speed doesn't mean it's doing a complete system analysis and saying, at this very moment, I should give you this many gallons per minute, because that's what everything tells me. They're not that smart, okay? They're not that smart. In fact, smart pumps might be the worst name we've given these things. I've heard trainers out there say, oh, it's a smart pump. You just put it in and it figures everything out for you. No, 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 no. Here's a very dangerous statement I've heard people say. Well, they take the thinking out of it. They do the thinking for you. No, and no, they don't take the thinking out of it. If anything we've been trying to share with you over these past several weeks about hydronics, and the fact that you guys are here means you understand this. We don't want to take the thinking out of hydronics. If anything, we want to put more thinking into hydronics. So we purpose choose our products. We purpose choose our components. It's selected for a purpose, all right, to create an end result where the whole is greater than the sum of the parts. That requires thinking. And Glorioski, Captain Kilowatt, they don't do the thinking for you. They can't. It's a stupid inanimate object. It has some cool technology in it that if you know how to utilize it, it will do pretty cool things for you. That's the thing you got to understand. All right. So they don't take the thinking out of it and they don't do the thinking for you. Those are two very dangerous statements that I've heard people make. Even more. All right. Hey, you push the button, it does everything you want. It figures everything out for you. Life is pain. All right. Life is pain. And anyone who says otherwise is selling something. All right. That's not how that works. Okay. I guess auto adapt. We have active adapt on our circulators. It's the same thing. That is not how that works. You don't just push the button and walk away and it figures everything out for you. That is about as opposite of what that button does. All right. So we'll explain that as well over the course of the next couple of weeks. And then the worst one I've heard is, well, it's the magic pump. This thing's, you're going to love this pump. It's the magic pump. If somebody has to use the words magic to explain how something works, they really don't know. Okay, just so you can take that one to the bank. These things are not magic. Okay.
Yeah, we call it PFM back here in New York.
PFM.
That's what we put in all the circulators. PFM. Yeah.
I got pure and magic. I don't know what the middle one means.
Well, you're in New York. You're in New York. There you go.
Okay, flip it. I'll go with that. Okay. So yeah, you'd like to think all of these things are true, wouldn't you? But they're not. Now, where do these myths come from? That's a good question. And let me ask you guys, and please type this in. Have you heard any of these myths? And where do they come from? All right, where do they come from? It just strikes me as so odd. All right, it strikes me as so odd for these things. That people will take this grand technology and try to super simplify it just to sell it. All right.
Or anything else, guys. Any other myths that we didn't already mention?
Right. Okay. We hear from manufacturers, bad factory salespeople. I've heard how a myth that I've heard how efficient they are. Okay. Yeah. There's just a lot of different stuff out there that comes from, I think, from people who are tasked with selling these things, but don't really understand the dynamics of systems in general, number one, but also how the particular product works in different situations. To me, that's where it comes from. You got to understand systems and the dynamics that exist within the system, and you've got to understand the technology and what it does and what it doesn't do. And Nicholas, you're absolutely right. Very few people read the manual, right? Because it's little words and manuals. Most instruction sheets, who are they written for and who are they written by? Okay, they're usually written by engineers for the legal department. Okay, if you think about it, that's kind of why nobody reads them, because they don't make any. They're hard to. It takes a lot of work to read typical instruction manuals. All right, so why go variable speed? Let's get down to it. Why would you use a variable speed circulator? Well, that's a pretty good question. Yeah, for some people, it might be for the same reason why the guy that lives on that island has a car, because he can, right? Because he can. And that is a good question. And the reason you should use a variable speed circulator is that when applied properly, they can enhance the economy of operation, the overall system efficiency of that system. They can make a good system better, but they don't. Like here, the automatic self-adjusting from installers, says Manson. Yeah, you hear that, but that's not what they do. they're not automatically self-adjusting. They do specific things. And again, we'll discuss that. But yeah, thank you for chiming in with that, Manson. We hear that too. We hear that too. Now, the best applications for variable speed circulators on residential applications is going to be for zone valve jobs. Regardless of the type of variable speed circulator you're talking about, delta T or delta P, either one. All right. When zone valves close, more often than not, the circulator will slow down. There are instances where it doesn't, and that's a system curve, pump curve thing. But when zone valves close, by and large, the pump will slow down. When zone valves open, by and large, the pump will speed up. Okay. Changing its speed, changing its electrical consumption, and changing its flow, not based upon the need, but depending upon the type of circulator you're using, but based upon a mathematical algorithm. All right. So zone valves is a no-brainer. You speed them up, you slow down. Now, here's a question that I'd like you guys to answer. Please type in your answer to this one. Would you use a variable speed circulator as a zone pump? And why or why not? Let's hear from you guys. Would you use a variable speed circulator as a zone pump? And why or why not? Let's hear what you guys have to say, because this is always a really compelling question. And the answers are just pouring in.
Pouring in fast, man.
Pouring in fast. As a zone pump, single zone, as a single zone pump, Nathan. Yeah. We got no, because it's not one zone, not necessarily, but it would deliver the correct flow without reading pump curves, Carl. We'll discuss that. Yes, to match the flow to the heat load, Jean-Luc says. No, says Nathan. Okay. We got one Zvi, only a delta T pump. Okay, hugs coming your way, buddy. Okay. Yeah, okay, good. No, would use on-off zone pump or open-closed zone valve and ECM at the boiler. No, because it's a single zone. Okay, interesting answers and interesting answers. And to really dive into this, we have to discuss the basic difference in operation between a delta T variable speed circulator and a delta P variable speed circulator. There's two different kinds, and Taco's the only company that sells both. Okay. A delta T variable speed circulator comes with sensors. One goes on the supply and one goes on the return. And the input, the information it uses to vary its speed is temperature. Meaning we're trying to get, what it's trying to do is to maintain the delta T between the supply and the return water, or the system delta T, that 20-degree delta T or whatever it was we designed that system for. All right. So it's going to speed up and slow down to maintain that 20-degree delta T within the system. So think about in a zone valve system for a minute, okay? That pump's pumpulating, zing, 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 going around, and the zone valves are all open, right? And the temperature sensors are picking a 20-degree temperature differential between the supply and return. All is good with the world. One zone valve closes, okay? One zone valve closes. Now, all of a sudden, we're not taking as much temperature, as many BTUs out of the fluid. So that return water temperature is gonna want to go up, right? That delta T is wants to get a little bit smaller. We're not taking as much energy, so the water is going to come back a little bit warmer than it was. Well, the sensor is going to pick that up immediately and going to tell the circulator to slow down to maintain that 20 degrees. Another zone valve closes, return water temperature starts to creep up a little bit, the delta T starts to snug up, the circulator slows down. Zone valves open, the exact opposite happens. All right. Now let's put that same circulator in a zone pump situation, a single zone. Okay, a single zone. And let's say it's 10 degrees outside, and that circulator is pumping away at a certain speed, maintaining a 20-degree delta T. What's going to happen when it starts to get colder out? Let's say it goes from 10 degrees above to 10 degrees below over the course of an hour. Just give as an example. Well, as it gets colder out and we're pumping at a certain speed, we're going to start taking more energy out of the fluid, right? That return water temperature going to start to go down a little bit, and then delta T is going to start to get wider. What does a delta T pump do then? It starts to speed up. Okay, it starts to speed up. So a delta T pump, when used as a zone pump, will in fact vary its speed based on the weather. Okay, understand delta T pump doesn't care what the water temperature is. It just cares about the difference in the supply water temperature and return water temperature. What's the temperature of the water going out? What's the temperature of the water coming back? We'll let the boiler figure out what that should be. It's just watching the difference. Okay, and then what impacts the return water temperature is basically heat load. As it gets colder out, the heat load goes up. I need to deliver more BTUs. I'm going to pull more BTUs out of the fluid. That water temperature is going to want to go down. I need to deliver more gallons per minute. So in that respect, a delta T circulator could be used as a zone pump. A delta P circulator is that P stands for pressure. It's a pressure differential circulator. The information it uses to change its speed is pressure differentials, changing pressure differentials within the system. It's set up to maintain a specific pressure differential within the system. So let's say all my zones are open, pump's going at a certain speed, all of a sudden a zone valve closes. That impeller is now starting to spin against more resistance because I've closed a zone. That's a signal for the circulator to slow down to maintain a specific pressure differential. Another zone closes, it slows down. Zone opens, it speeds up, but it's pressure differential. Now, if you were to use that as a zone pump, there's nothing in a single zone that's ever going to tell the impeller that there's more or less pressure differential. So when used in that respect, it's not a variable speed pump. It's a fixed speed pump. That doesn't mean you shouldn't use it. Okay. This is where knowing what these things do and how they do them and what you can make them do now starts to make that a viable alternative as a zone pump. Just because it doesn't vary its speed doesn't mean it can't find its happy place and operate in a very efficient and effective manner for your system. And that's the kind of stuff we're going to get into. That's the thinking that has to go into this. All right. Let me know if this makes sense to you, and let me know if any questions you guys might have so far. Okay, about what we've talked about. Because what we're going to get into now is electrical savings. One myth I want to bust right now is the electrical savings. But let me know if that makes sense. Robert, thank you. I'm glad that helps. But let me know if this is new information for you and if it's useful, if it makes sense. Because again, when you really know what these things do, you can make them do some pretty cool things. So let's talk about electrical savings. All right. Let's do some math. All right. Jimmy DePalma, I think you're the one who actually turned me on to this math formula, because you said you had a customer who was thinking of, he was a wholesaler and he wanted to swap out his 5 circulators, his 5 TACO 007s on his heating system for 1 ECM circulator and 5 zone valves, because he wanted to save a ton of money on his electricity so he could buy a new set of golf clubs. All right. That was the deal he made with his wife. And he wanted me to figure out how much money he was going to save so he would know, what neighborhood he should be shopping in, okay, for his golf clubs. And so let's do some math here. And this is just basic electrical consumption math formulas here that we're going to deal with. If I have 5 007s, all right, at 80 watts a pop, well, that's 400 watts worth of pumping power. To estimate electrical consumption, I need to turn watts into kilowatts, right? And we're going to do that by dividing by 1,000. So 400 watts divided by 1,000, well, that's 0.4 kilowatts. That's the use. That's the consumption of those 5 circulators, 0.4 kilowatts in total, all 5 of them together. Now we have to turn kilowatts into kilowatt hours. We have to get a good estimation of how many hours over the course of a heating season these things are actually going to run. And fortunately, we don't have to guess. Is it AHRI? I think, no, it's the Gas Appliance Manufacturers Association publishes this map, which is kind of interesting. And it's just a map of our country. Notice no red or blue, okay? It's because we all need heat, all right? And what this breaks it down to is the estimated number of run hours for our heating equipment in these different areas, okay? So if we go up here to Maine, okay, we're in that 2,500 hour range, okay? And that 2,500 hour range goes through, New Hampshire, Vermont, part of Massachusetts, through New York, and all the way up here into the Rocky Mountains. All right. If we get up into these northern climes up here, and in part, obviously Canada and the upper portion of Minnesota, the tip of the mitten, and the upper peninsula in Michigan, now we're talking about 3,000 hours. It doesn't.
Hey, John.
And you might look out here on the northern coast of California, southern coast of Oregon. You're looking at 3,500 hours. This map doesn't tell you how cold it gets. It just tells you how long the heating season might be.
Yeah.
All right. So that's kind of where we're at here. So for our purposes, even though Jimmy was down here in New Jersey, we're going to use 2,500 hours because we really want this guy to get a good set of golf clubs. All right. So let's see where we're at. 0.4 kilowatts times 2,500 on hours, that's 1,000 kilowatt hours. Now you simply multiply that by your cost per kilowatt hour. In this case, we're going to use a high national average of 15 cents a kilowatt hour. So what we're finding here is those 5 circulators cost about $150 a season to operate. That's not per circulator, that's all 5 of them in total. $150 a heating season, which we'll identify as the beginning of October through the end of April. That's 7 months. Define a monthly average, divide 150 by 7, and that looks like it's about $21 and change per month. All right, $21 and change per month to operate those circulators. Not all right. All of a sudden, this dream of new golf clubs is starting to look like the bargain bin in a used golf shop. All right, so that's $150 a year. What if we didn't go super duper ECM? We just went with 1 regular 007 and 5 zone sentry zone valves, and you can see where we're going here. We're down to 87.2 watts. All right, and that comes out to 0.0872 kilowatts, 218 kilowatt hours compared to 1,000. That's about an 80% reduction in electrical consumption. And do you know why it's an 80% reduction in electrical consumption? It's because we have an 80% reduction in the number of circulators. No, it's not magic, Dave. It's not magic. It's an 80% reduction in the number of circulators. All right. 1 circulator is 80% fewer circulators than 5 circulators. All right. If Mary had 5 circulators and Rick took 4 of them away, how many circulators would Mary have left? Just the 1. She'd need 5 zone valves, and Rick has those. All right. So 218 kilowatt hours times 15 cents a kilowatt hour. Now we're talking $32.25 a year, or over 7 months. God, $4.50 a month. And we didn't go ECM anywhere. All right. So we got $4.50 a month compared to $21.50 a month. So what did we just do? We saved you $17 a month. All right. What can you do with $17 a month? Not saying that you shouldn't. It's a great thing to cut your electrical consumption and cut your bills in every way you can. But we're not talking life-changing money here. I mean, what can you do? What can you, before the pandemic? What could you do with $17 a month? Maybe go to the movies once by yourself. Right, by yourself. Or go to a matinee. 17, you skip the popcorn, maybe you could bring a date. I don't know. All right. Now let's throw the ECM at the equation. All right. And let's say it averages about 20 watts. It's going to speed up and slow down. Averages about 20 watts. You see where we're going here. So that's 68 kilowatt hours. All right. $10.20 a year. Now here's where the marketing departments get on my nerves, because the marketing department will say, hey, $150 compared to $10.20. And you think, oh my God, these things do save a buttload of electricity. If I got rid of all 5 of those, man, wow, I just saved so much. But they're comparing 1 circulator and 5 zone valves to 5 circulators. It's a bogus and almost, I think, irresponsible comparison. All right. I've seen other comparisons where they compare running an ECM circulator to a standard efficiency circulator, but it's running for 6,000 frickin' hours. Meaning it doesn't shut off. I said, well, why would you run a circulator for 6,000 hours? That doesn't make any sense. All right. It doesn't make any sense. All right. Question from Paul. What was the consumption of the 5 circulators? That was $150 annually. It was 1,000 kilowatt hours. 1,000 kilowatt hours. So yeah, absolutely. It was bigger. This is 68. That was 1,000. In terms of dollars and cents, watts each, 80 watts. Okay. Takeo 007 is an 80 watt circulator. All right, it's an 80 watt circulator. So it's kind of interesting. A lot of guys say, "Oh my God, I'm going to save a ton of money." Say again?
And as we saw last week, a lot of times a 007 is way too big for most of your projects if you got 5 pumps in there.
For sure.
So it's not like you need to go to, a 14 because you took out 5 007s. 007 might still be able to handle the load. So.
That's right. That's right. And Paul says, so the single with 5 zone valves has to be larger than 80 watts. Oh, it's an 80 watt circulator with 5 1.44 watt zone valves. So it was like 87 point something, I think, right? If that makes sense to you, Paul. Yeah.
Yep. So. All good.
You got it? Oh, did you just say that? See, you were answering the question while I was reading the question, so I didn't listen to you answer the question, so I came in and answered the question. All right. Inconceivable.
That's his.
Okay.
I've been watching way too much television
Too much
over the last day and a half. All I have to say to you, Dave, prepare to die. All right. No wonder everybody was quiet. I don't have time to listen. I'm too busy reading and trying to come up with the answer. I'm thinking about what I'm going to say next. So people look at that and go, well, why the hell would I want to use one of these things? What's the point? The point is we start using these things to really make a difference within the system. Electrical consumption, electrical savings is nice. We put that under the realm of nice, okay? It's the cherry on top of the sundae, okay? It's just nice to have. It would be inconceivable for someone to replace 5 perfectly good operating circulators with 1 ECM and 5 zone valves in order to save electricity. It would make no sense. All right, these things still have a ton of life in them, and what you'd have to pay to do that, to basically repipe your boiler, you're never going to offset the cost with the savings. It just doesn't make a ton of sense. Okay. All righty, very good. So, well, here we go. Let's do the Takeo trivia question of the night, shall we? Now, in The Princess Bride, everybody who's seen The Princess Bride, it's a great movie. Forrest Gump, you've seen Forrest Gump. Forrest Gump is a great movie. And nonsense aside, House of Cards on Netflix was a pretty interesting and thrilling TV show. All right. The trivia question we have on the table is, what do all 3 movies have in common? There is a common thread through all 3 of these movies. What could that common thread be? Type in your answer. All right. I know you're all going to be Googling and all that stuff, but type in your answer and you will be entered into our prize raffle for next week. We got our prize raffle for this week coming up to the end based on the trivia question from last week. So that is your trivia question. What do Forrest Gump, Princess Bride, and House of Cards have in common? There we go. All right. And Mike Hansen asked a pretty good question. If the 007 is usually oversized, why doesn't Takeo promote a 005 style pump? Hey, we tried. We tried with the 005. Nobody bought it. You know why people didn't buy it? Because it didn't perform to the level of the 007, and nobody was having a problem with the 007. So it's interesting, and people don't buy on price.
Yeah. And also to think about it back in those days too, when the 007 came out, what was the 007 replacing? Your B&G 100, right? Yeah. And I'm sure if anybody has pulled out a B&G 100 in the last couple of years and replaced it with a 007, and the homeowners saw you doing it, they said, no way that's going to heat my house. So now think back almost 50 years ago in the 70s and 80s, when we were, the 007 really started gaining ground. Then all of a sudden we came out with the 005 and said, oh, here, by the way, you're already putting in a smaller circulator. Try a different, smaller one. Yeah, no. I'm good. Like John said, the 007 wasn't broke. I'm not going even smaller now. So that's how, and still we were looking at single zone systems, and the 007 was more than enough, circulator. So now, let's take the next 20 years, and people are starting. We see in the last 20 years how many zones are in a house. They're increasing. just in this short time period compared to, 50 years ago where it was still 1 for 1. So
Very
my
good.
rant is done. Yep.
All right. I'm not going to repeat it like you never said it either, because that would just be embarrassing at this point. All right. Have fun storming the castle. I love that movie. All right. Let's talk about what happens when zone valves close. When zone valves close. Remember, we're talking about a fixed speed circulator, or the fixed speed circulator. We have to understand the concept of system curves and pump curves as we move forward. So when zone valves close, it's kind of like a big traffic merge, or actually think of it as a big traffic jam. Think about the biggest highway near you. Let's say you got a 4-lane highway with all 4 lanes going in one direction. All right. And let's say it's rush hour and you have traffic like we show here on the picture, and it's all nose to tail. Okay. All the cars are nose to tail, and all of the cars are driving at the posted speed limit. Let's be theoretical here. Everybody's going the speed limit. No one ever goes faster than the speed limit. So everybody's going the speed limit. Nose to tail, that's the maximum amount of cars you could have moving on that highway, right? It's your maximum cars per minute flow rate, as it were. Okay. Think about that. Now we got 4 lanes, right? Well, what happens if there's a fender bender in one of the lanes and all of a sudden that lane's now shut off? I still have 4 lanes worth of traffic, but I only have 3 lanes for that traffic to go through. So my cars per minute flow rate has to go down because of that little traffic jam. My cars per minute flow rate has to go down. All right. That's number one. Number two, at that choke point where the 4 lanes are going into 3, that's where the traffic starts to back up, right? That's where the traffic starts to back up. Keywords, back up. And thirdly, what's happening inside the driver's compartment of every one of those cars? You're starting to get guys getting really annoyed with a little bit of road rage. You could say the pressure in their head is going up. Carefully phrased there. So let's think about that. All right. The traffic flow rate goes down. The traffic itself backs up, and the pressure in your head is going up. Perfect analogy for what happens in a real world hydronic system. So again, design conditions, even not design conditions, doesn't matter. All zones calling, all my zones are open. That's the maximum gallons per minute flow rate I could possibly have in that system. All right. It's the maximum flow, and it's the least overall resistance to flow because all the doors are open for the water to flow through all the zones, right? As a zone satisfies, as a door closes, I have fewer holes for the water to go through. So that's increasing resistance to flow, and 3 or 4 lanes are going to be merging it down into 1 or 2. All right. So in that case, my flow rate has to go down. My flow rate has to go down as zones close. All right. Just because there's less room. It doesn't matter if it's a variable speed pump or a fixed speed pump. Zone valves close, flow goes down. Okay, the flow changes as zone valves open, whether it's a variable speed pump or a fixed speed pump. All right.
Hey, Mike. Mike wants to clarify something. He's saying your analogy, is that a shouldered seat? It's like a shoulder condition. It's not a design load. So clarify that for Mike.
If it's not
Mike is talking about the traffic in New England where you get to use the shoulder of the road in some parts of Massachusetts. I believe that's what he's talking about there. Right?
That's not how I interpret it, but you're probably right.
No, but Mike, explain. We have mixed interpretations to your question, Mike. So let's hear what you have to say. And Doug says, "What is a speed limit?" I'm sorry, that's traffic school. You're gonna have to go to a different class to learn that one. All right. So what we have going on here is a system curve shift. Now, we haven't talked about system curves yet, really, have we? A system curve, or maybe we did. A system curve is the hydraulic fingerprint of a piping circuit. All right. We figure this stuff out. Actually, yeah, we did talk about system curves last week. It's the hydraulic fingerprint. Okay. If we do the math and we find, like in a zone valve job, that I'm going to need 7 gallons a minute, that I'm going to need 7 gallons a minute at 5 foot ahead under design conditions. All right. I know 7 at 5, I know 0 at 0, and mathematically I can calculate what would the head loss be through that piping circuit at, say, 3 gallons a minute. What would it be at 5 gallons a minute? I know what it is at 7. What would it be at 10? What would it be at 15? Okay. And once I have those points on the plot, I connect the dots, and there's my system curve. There's my system curve. With a zone valve system, I got a whole bunch of different system curves, one system curve for every combination of zones that could be open at a given point in time. For example, a 3-zone valve system will have 7 different system curves. All right, zone 1 by itself, zone 2 by itself, zone 3 by itself, zone 1 and 2, zones 1 and 3, zones 2 and 3, and zones 1, 2, and 3. That's all 7. I'd have 7 different system curves, okay? And as we said last week, what makes system curves important is because systems operate where system curves intersect pump curves, all right? So a seven system curve system for that 3-zone zone valve system will actually have 7 different points of operation along a pump curve. It's going to operate in 7 different areas on that pump curve. Let's take a look. And here you go. We add the circulator. So here's a 007. All right, here's a 007. I need 7 gallons a minute at 5 foot ahead. And when I put this circulator on, I'm not working here at 7 at 5. I'm actually working here at about 9.5 at what looks to be about 8 feet ahead. All right, that's where it's actually going to work. As zones close, the system curve is going to back up the pump curve like traffic backs up. We're going to back up the pump curve to where that intersects here. Another zone closes, we go back here. Another zone closes, we go back here, and so on and so on. So the flow, every time that zone valve closes, the flow goes down, but because I have to work on this pump curve, the head pressure differential created by the circulator goes up. That's just how it works, okay? Because we have to work on the system curve, we have to work on the pump curve, and energy in equals energy out. It's a fixed speed pump at this point. It's not making any changes. But again, the flow is going down simply because I don't have as many holes. Now, what you have here with a 007, which we're going to identify as a relatively speaking flat curve pump, high flow, low head, flat curve. What this tells us is a big difference in flow going from 9.5 maybe down to 1 or 2. A big difference in flow is resulting in a relatively small difference in head pressure differential being created by the circulator. That's important. Why is that important? Well, let's look at the same system, but with a steep curve pump. With a steep curve pump. Now, this is a TACO 0015 standard efficiency 3-speed with the setting set to contractor, no callback mode. Same thing for a 00 or a Grundfos 1558, a B&G NRF 22. Take your pick. They're all essentially the same. All right. And we set it to contractor, no callback mode. Same system, different pump. Same system, different pump. Okay. And again, out here, I'm at 9.5 gallons a minute, about 8 feet ahead. It just happens to work out to the same place. But now look where we're intersecting. We're intersecting up here at 5 gallons a minute. With that one smallest zone calling, I'm way up here at about 2 gallons a minute, where before I was down here at maybe 1.5. Okay, so again, flow, I'm over pumping in terms of flow, but that's part of the problem here. As flow goes down, look what's happening to the head pressure differential. As flow goes down, I get big changes in head pressure differential. That's the difference between a steep curve pump and a flat curve pump, boys and girls. Flat curve pump, big changes in flow give you very small changes in head pressure differential. A steep curve pump gives you very large changes in head pressure differential. Why do we care about that? Why do we care about that? Well, have y'all ever had a situation where you needed to deal with banging zone valves, or perhaps even zone valves where they couldn't close against what the circulator was doing and you had ghost flow? Zone valves don't bang because they're angry with you. Zone valves bang when they try to close against that kind of head pressure differential. You'll go stung, and you get like this water hammer kind of thing.
How do you
That's not
fix it?
supposed to happen. That's not supposed to happen, okay? And the reason it's happening is because I'm working way up here in terms of head pressure differential, as opposed to way down here in terms of head pressure differential. It's not a problem with the circulator. It's not a problem with the zone valve. It's a problem with the marriage between the two. Flat curve pumps and zone valves go together like cake and ice cream. Steep curve pumps and zone valves go together like tuna fish and ice cream. There you go.
So if you've had banging
makes
zone
sense.
valves, if anybody out there's ever had the banging zone valves, what do? How do you make that noise go away?
You're
Well,
just trying to get me
yeah,
riled up, aren't
one
you?
of the what? No, 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 no. You know, I mean, as John was just saying, yes, change the circulator. But if you've ever run into it before, or if you've had other guys fix it, how did they do it? So I'm just curious as to some of your answers out there. Yeah. Yeah, don't go
Sorry.
there, Mike.
I'm just trying to collect myself. Yeah, Mike,
Yes,
you're
yes.
just poking the bear. Just keep poking the bear, Mike. That's all you got to do.
Well, I've heard it several times that guys go and pull the spring, one of the springs out of the zone valve. Yeah, don't do that, So all you're going to do is make it worse, and you're going to get a lot of bleed by that. So I just want to make sure that people know that, because I've heard that as a legitimate fix a lot of times, and what ends up happening is that you're going to get blow by of that zone valve. So don't be pulling a
Yeah,
spring.
you do actually solve the problem of the banging zone valves, because it will no longer bang when it's trying to close, because it can't close. So you are solving the banging zone valve problem, Dave. Haha, you got nothing to say about that, do you?
Inconceivable.
Inconceivable. All right. So what do we do about it? What do we do about it? Right? Never go against a Sicilian when death is on the line, says Dave. So what do we do about it? Well, the first, stay flat. Why create a problem? Use a flat curve pump. Zone valve jobs need flat curve pumps. Use a flat curve pump. Why create a problem? It makes 0 sense to create a problem, and then have to solve it. Just use the right pump for the right job. All right. Detour. All right. That's your pressure differential bypass valve. And a lot of people will look at this and say, well, that's the right way to do it. That's how we've been doing it since we started using 3-speed pumps, because that's what we'd have to do. Well, no. Pressure differential bypass valve does one thing here, is it turns a steep curve pump into a flat curve pump. And if that's what it was doing, if that's all it's doing, it's only turning a steep curve pump into a flat curve pump, well, why the hell not use a flat curve pump in the first place and skip this step? Why have the added cost of buying, installing, and then trying to figure out how to set the darn thing when you could just put in a flat curve pump and be done with it? All right. So
Hey, John.
again, a lot of people use it, but 99 cases out of 100, to me, the pressure differential bypass valves I've seen, it's a Band-Aid for a self-inflicted wound. Yes, Richard.
Did you purposely turn your video camera off?
Yes, I did.
Okay, very good.
I got a little notification that it might be causing my internet to slow down.
Okay.
So I turned it off.
Cool.
I'm now making very, very obscene gestures to you, just so you know.
Oh, thank you.
I'm not. You know that.
He's only doing it to me.
Yeah, that's right. And then the last solution is simply to adjust and adapt, and that's your variable speed solution. That's the variable speed solution. All righty. So here's the point of variable speed circulators. No matter what people tell you, it's still system curves and pump curves. Systems operate where system curves and pump curves intersect. What variable speed circulators allow us to do is to try to in the delta P case, it allows us to better match a pump curve to a system that needs change, that needs the ultimate in flat curve pumps, like a zone valve system. You want a flat curve pump. A delta P pump in constant pressure differential is the ultimate flat curve pump, and you get to choose different sizes. All right, that's a fantastic a way to use that. All right, if you use a delta T variable speed circulator, now you have a circulator that can, for the most part, adjust its pump curve to meet the needs of a system, which makes it different from delta P. So there's two different solutions here to the same problem. That's the point. Again, do you want to put in a circulator that could conceivably cause some problems? Inconceivable. Or do you want to put in a circulator that could in fact enhance the efficiency of the system? You could put in a circulator that could cause you problems and limit the efficiency of a system intentionally, or you could put in a circulator that could enhance the efficiency of the system and not create the problems. That's the point. That's the point of variable speed circulators. And now we get into, again, delta T or delta P. All right, I just wanted to give you a brief, look-see at the delta T and delta P offerings that we have, and then next week we're going to do a deeper dive into these things. But the delta T circulator is the VT2218. And Rick, why do we call it the 2218?
Well, look at the line B. It's the shutoff head is 22, and then look at the runout down on the GPM, and that's 18. So that's my guess.
I think you're right. VT means variable speed temperature. All right, temperature delta T, VT2218. Now what you have here is line A is your minimum speed. It never goes slower than that. No matter what anybody else says, it doesn't go any slower than that. It has a floor. It has a floor, and it also has a ceiling. It can't go any faster than that. But it will automatically adjust itself anywhere in between these two lines in order to maintain the temperature differential that you have set the system for, what you've designed it for. If the system's designed for a 20-degree delta T, take it right out of the box. It's set for a 20-degree delta T. You don't have to do anything. If it's a radiant system that was designed to a 10-degree delta T, you can adjust the delta T down to 10. If you wanted to run it at 30, you could. I mean, depending upon how the system is designed. All right, what was the design of the system? All right, now how does this guy work? Again, that zone valve system, 7 gallons a minute at 5 foot ahead. That was all zones calling, okay, under design conditions. Well, by golly, that's where the system's going to run, right there. Here's my pump curve. Pump curve is going to be right there. It's going to set itself right there on the coldest day of the year, all right, on the coldest day of the year. Now, let's say my smallest zone was 1 gallon a minute at 4 feet ahead. So that's right there. And here is my performance curve with just the one zone calling. So under design conditions, quote unquote, coldest day of the year, as zones open, it'll go faster till it reaches there. And as zones close, it'll go slower until it reaches there. And it'll find that level automatically. Now, as it gets warmer out, remember, GPM equals BTUH divided by delta T times 500. We know the BTUH is going to change, right? The BTUH is going to change based on the load, based on how cold it is. As it gets warmer out, the BTUH starts to go down. The delta T's fixed. The flow rate has to go down, man. That's just math. So both of these lines are going to drop, okay, as it gets warmer out. At some point, when the one smallest zone is calling, I'm at a 9-watt fixed speed pump, and it'll go up to wherever it needs to be with all zones calling and then back down. But as the winter goes on, this high speed is going to drop, and you're going to find a situation probably about halfway through the season or about 50% load where you have a 9-watt fixed speed pump. That ain't bad. Okay, nope. That is not bad. I would suggest to you that a 9-watt fixed speed pump is more beneficial both electrically and system-wide efficiency than a delta P pump that's not set up properly. All right, I would suggest that that's still going to work out better in operation than an improperly set up delta P. In some cases, maybe even a properly set up delta P. All right. So just something to think about. Just because it's not varying its speed doesn't mean it's not doing the system some good. So at some point over the heating season, you're going to have a fixed speed 9-watt pump, and you're going to heat that house for most of the heating season with a 9-freaking-watt pump. Now we're talking about some electrical efficiency here as well. All right. Now jump to delta P. This is our Takeo 0015E3. It's for people who really like 3-speed pumps, and we understand it's a 3-speed world in many cases. What the 0015E3 does, it's a constant pressure delta P circuit, meaning it's less technology, it's less expensive, number one, no sensors or anything, number two. But what we have is 3 settings. We have low, medium, and high. High is full speed, fixed speed. It's a full 44 watt fixed speed pump. That's your contractor no callback mode, man. Medium speed is a constant 10 foot of head constant pressure. So it's kind of like the ultimate flat curve pump at 10 foot ahead. This is the variable speed range. Out here is fixed speed range, depending upon where the system curves intersect the pump curve. All right. And then down here at low speed, it's a 5 foot ahead constant pressure variable speed circulator. So again, which one do you use is going to depend on which one you need. For our 7 gallons a minute at 5 foot ahead job, hey, I'd go right to low speed, and that's about as good as it's going to get with that pump. Okay, that's about as good as it's going to get. All right, is it as good as the Delta P pump or the Delta T pump? No, it's not. Is it close? You know what? The smaller the system, the closer they get to in terms of benefit. All righty. Last thing I want to share with you here is how does this thing actually change its speed? How does it know? What's the inner workings? So this is a Delta P constant pressure pump. And let's say I'm going to set this up at 10 foot ahead, my 10 foot ahead constant pressure. And here's my 7 gallons a minute at 5 foot ahead. And I've set it up incorrectly. I didn't pick 5, I picked 10, just for illustrative purposes. So again, system curves and pump curves, it's going to work right here. All right. Now, all of these lines here represent programmed in pump performance curves. So what you have with this circulator is a bunch of different pump performance curves. And we can jump from one to the other based upon, basically it's amp draw and programming, but it's resistance against the impeller. So right now, I'm working on this pump curve right here at whatever wattage that might be. Now, when a zone closes, all right, when a zone closes, this zone closes, I get a new system curve. And what's going to happen is going to be like a nanosecond. It's actually going to behave like a regular circulator and work up there for just like a nanosecond. It's still working on the same pump curve, but there's now a new system curve, a new point of intersection. The impeller senses that greater pressure differential, okay, that greater resistance. The mathematical programming says, we don't want that. We want you to go right back down here. So what it's doing, it's actually going up here and then whoop, right back down, but it happens so quickly that it looks like it's just smoothly jumping across like so. Next zone closes, same dance. We go up here. Now we're not going to work up there. We're going to work down here, and so on and so on. So what you'll see is with my one smallest zone calling, I'm working on this pump curve. With all of my zones calling, I'm working on this pump curve, and there's a wattage difference between these. All right. The higher the speed, the more wattage you use. The lower the speed, the less wattage you use. Okay. And that's all it's doing. It's not calculating flow. It's not giving you the right. It's not saying, all right, here's the system going. This is the exact right flow that you need. It doesn't. No, doesn't really care, because your flow, as we look, might be for one zone calling, might be 1 gallon a minute at 4 feet ahead. That might be where you really want to be, or maybe right down in here. That might be where you really want to be. You're not getting that. You're getting that, and that's that. Okay, that's how it works, because it's working on a pump, working on a fixed pump curve. If I had chosen the 5 foot ahead constant pressure line, I'd still have the same deal, but I'd be working in a much more electrically efficient mode at these much lower speeds. So again, knowing what you've got in your hands and how it works and how to make it work for you is the thing that's going to matter the most. All right. How are we doing out there, peoples?
Good.
Oh, I'm just doing fantastic.
Beauty.
All righty then. You Sicilian. I'm more Sicilian than you, and I'm not really that Sicilian. All righty. So what is The answer, it's Robin Wright. Most of you got that. Someone said you gave it away by having the picture of her. Yeah, I know, but we didn't want to make it too hard. And actually, I did this and showed this to my wife. I showed her the picture, showed her the questions, and she's looking at this thing. And she says, I have no idea. So I figured if she didn't know, maybe it'd be a good question. But yeah, Robin Wright, Robin Wright, Robin Wright. And I was going to put in Wonder Woman here too, but I didn't have enough room to put all three pictures in. So
30
yes.
years apart from those two, from the last
Yes.
two pictures. Yeah, 30
That's right.
years. Yeah.
That's right. She's been around a long, long time. She was actually, I think she got her start on remember the nighttime soap opera Santa Barbara?
I do not.
I don't either, but that's where she
Nope.
got her start. I
Oh,
read
okay.
that on Wikipedia. So she played Princess Buttercup. She was Jenny in Forrest Gump, and of course, Claire Underwood in House of Cards. All right. So coolness. What are your questions there, folks? How are we doing out there? What was this a useful
Kinda
program?
quiet.
Yeah,
Kinda-
once we
yeah,
started
kinda quiet.
talking about pressure differential bypass valves, everybody got kind of quiet out there.
Yeah.
All right, what do you got? What's going on out there, people? Let's have some what do you got for questions or comments or answers?
And while you guys are typing in any questions or comments or anything like that, I need to give some crap away.
Oh, yes, you do, for last week, right?
Whoops. So I just stole the screen. So just wait till I get it up and running here.
Inconceivable.
There we go.
There it is.
All right. So yes, last week, I don't even know anymore
let me
what
look that up.
the question was last week. We had, Snoopy's playing. What was
That's
the
right.
name of
The Sop
Snoopy's
with
playing?
Camel, yes.
A lot of people got that and got it quickly too. I was surprised on how fast people answered that. So let me get that screen up here. Let me hit that tap to spin. Let's get that rolling. See who our winner is going to be. Is it going to stay on Jonathan? There it is. It's on Jonathan.
All right, Jonathan.
All right, Jonathan.
Hey.
Excellent. So while you're here, while you're still online with us, Jonathan, I know I saw your name here already tonight. Just type in your mailing address. I will make sure I get the prize pack sent out to you right away. Thank you.
Very good. Awesome, man. Congratulations. See, watching television really does help, doesn't it? Right? Rick, you don't agree?
Well, some TV, absolutely, but most
There
of
you
it's
go.
just a sponge soaking all your brain and your time away. But
Well, hey,
don't get me wrong.
that's
I
no,
love
it depends on how you make use of that time. If you're learning stuff, like for me personally, I know more crap that won't make me a dime than anybody else I know. That's because I spend a lot of time watching television. A lot of these trivia questions, I didn't have to look them up. All right. That's a sad commentary on my life. All right. I knew Gilligan's first name because I just knew it. Okay. So yeah, that's it depends on how you use the information. To me, I think it makes you a more interesting and well-rounded person. But then again, I would think that.
My parents
All
never
right,
said that
next
to me
week.
from watching TV.
Say again?
My parents never said that to me. They just said I'm going to melt my brain.
Yeah, my parents never encouraged it either, but I was a rebel, I said I think I can make use of all of this information at some point later in life. I just didn't know how. All right, so next week, hopefully this was useful for you guys. Next week we're going to be talking about ECM and delta T, delta P. We're going to dive deeper. We're going to dive more deeply into those things. We're also going to talk about Bluetooth technology and the 0018E and how that can really be a game changer if you use it properly. I guess all of this is kind of leading up to the conclusion that, you know what, guys, the circulator might have more to say than overall system efficiency and economy of operation than we've ever given it credit for. And it's one of the things that you can help enhance the system efficiency. If you use the right circulator for the right reasons and understand how to make it work for you, you can make a good system great. All right? You can make a good system great. And it's all about understanding what they do and how they do them. how they do it. It's again, that whole thing about press the button and walk away. It's a great story. It really is a great story. It's complete crap, but it's a great story. You got to know how these things work so you can use them for your benefit and for your customers' benefit. So that's what we're going to talk about next week, people. All right. And thank you.
Yeah.
There we go.
Great story.
Great story. Isn't it a great story? All right. Some
Isn't it
reading
great?
and thinking is required, says Doug. You're absolutely right, Doug. I absolutely. Absolutely. All right.
Yeah. I mean, it's one of those things that I think about quite often when I'm sitting there driving on the road. And now that I'm not driving, I just stare out the window now. Now that I have a window, I left the basement. I'm upstairs now. I have a window to look out of. When you think about circulator technology, right? 007 was introduced in 1971. In the middle 50s was the Perfecta wet rotor circulators that we had. Other than making them 3-speeds, what other advancements have we made in circulators other than ECM, right? So you're looking at 60, 70-year-old technology that hasn't changed much. So that's where this the whole ECM variable speed world is. I mean, look at boiler technology in the last 15 years and where that's gone. That is just skyrocketing out of control. So circulators is due, so to speak.
That's true. And
okay.
Yeah, again, I mean, the 007 technology has changed over the years. It's improved, but it's still essentially the same performance as it was in 1974, 75. Your 3-speed circulators, really haven't changed much since 2002. Still the same thing. There's no new technology in any of those in terms of anything really. This is the new frontier in terms of making, of getting the most technologically advanced type of products that you can and making them work for you. Because again, this is one of those rare opportunities where we can use these things to really make a difference in our systems. And I've talked to guys, said, well, I use these things now and they're cheaper and they work. Why would I want to use this? This makes no sense. They're never going to make that money back. Whoa, that's not the point. The point is, it's not about making the money back, it's about making the system better. All right. And if we can enhance the overall economy of operation of a system, not a bit, it's money well spent. All right. That'll come back to you tenfold.
Yeah.
You guys have heard it too. A guy said, well, what if I'm more expensive on my job quote? Well, so if you lose a job because you included a couple of ECM circulators and the other guys had standard efficiency circulators, right? If that's not why you lost the job. If you think you lost the job because you had the more expensive circulators, that's not why you lost the job. You lost the job before the circulators had anything else to do with it.
Yeah.
They're not deal breakers. And Mike, absolutely, yes. Speaking of the 007, we lost Sean Connery over the weekend, and what a great actor he was. We had a Sean Connery double feature over the weekend at home on the Fire Stick. What did we watch? Watch Goldfinger and The Untouchables. Two great flicks. No, Mr. Bond, I expect you to die.
But he wasn't the original, and I can't remember the original's name. I'm sure you do because you have information in your head that's just it's there.
Well, they
wasn't
had some James Bond stuff on like British television, but in terms of feature films, he was the original 007.
I believe there was one movie. It wasn't the TV. I think it was one movie, wasn't it?
You're thinking about Casino Royale that came out in 1967. That was kind of a comedy.
Not that one.
Almost.
That was a spoof on it. Yeah, no.
Her Majesty's Secret Service. That was 1969. After Connery left, and that was George Lazenby. And then he lasted one movie, and then Connery came back for Diamonds Are Forever. And then they went on to Roger Moore. Yeah, it's on Her Majesty's Secret Service. That was 1969. That was a great movie. That had Diana Rigg in it, which I'll watch any movie with Diana Rigg in it. Right, who won the trivia this week? Brian got kicked off. That was Jonathan Fedorchak. Federick, Jonathan Federick. He won, and it was Robin Wright was the correct answer. There you go. There's a really interesting documentary on George Lazenby. I think it's on Netflix, about how he came to be 007. He wasn't an actor. He was in commercials and stuff, and he was kind of like a young guy living the high life in London. He was not from Australia, but he was, partying and playing, messing around with all, chasing women all over London and stuff, and kind of living a party lifestyle, doing commercials. And he somehow talked himself into an audition to replace Sean Connery, and it was actually pretty cool. It's on Hulu. Okay, you've seen it, Scott. Yeah, it's a really good documentary. It's quite funny, actually. It's really quite funny. And he said he had no problem stepping away from being James Bond. He had a seven picture deal for mega millions of dollars. He just walked away from it. He didn't want to do it anymore. So, Becoming Bond, that's the name of it. Really, really good thing. Yeah, Dr. No. Yep, Dr. No was the first movie. Then From Russia with Love. Goldfinger, really the first blockbuster, if you think about it. All righty. Any other questions, guys? We were talking about ECM pumps. We're talking about James Bond. This is always that let's kick it around and shoot the breeze and have a little tech gab. Hey, toolbox talk, if you will. Go for it, Rick.
There was some pictures floating around. I saw it probably on Facebook or LinkedIn or something, where there's a picture of 2 or 3 Perfectus that somebody took and said they were remodeling or something, but those were still working. And Dave, did you capture that? You probably saw that. I think Mike Miller had a copy of it.
Yes,
and,
I saw.
Can you pull that up? Show these as nostalgia and 100-year anniversary. I thought it would be something to show folks that haven't seen that. Some don't know what a Perfecta is.
Yeah, it was on Facebook.
Was it? Okay.
I think that was on Facebook. Yeah. Mike Miller, who's now the new czar of Canada for Taco.
Czar.
He is now he's going to be taking over for Jim Garrett up there. He's president of Taco Canada. Taco Canada. He's
the
they don't really have presidents. He's prime minister of Taco Canada. That might be it. He's going to lead a coalition management team. Yes.
Let's see. Where did I put it? I don't know. I lost it.
Okay. Well.
But so those Perfectas were the 152s, which was the second generation of the Perfectas. They got a little bit smaller. So it was, we joke about it. We call that the college football size compared to the NFL size. The Perfecta 1 was a little bit bigger of a circulator. It got a little bit smaller, meaning just less cast iron actually went into the 152s. And the dates on those circulators, I believe, was 1962. And wow. It was one of our first wet rotors, and it was still running. And I also had a friend of mine also had 2 of them in Rhode Island that were still running on a job site too. He called me up and sent me some pictures a couple of weeks ago too. So still out there going, man. Still out there going.
Yep, that's very cool. That's very cool. And Carl Carboni says you got your adult apprenticeship night class. So you got a whole bunch of guys out there right now.
Very good.
All right, all 16 of you. How you guys doing? Was this fun for you? I guess I love the idea that you're doing that for your class, Carl. Thank you. That's very cool. I hope we're helping you guys and not scaring you away.
Yeah.
From the industry.
We need you.
We definitely do. Because hey, look at the 3 of us. We don't have a lot of time left, The clock's ticking. We're approaching our expiration date.
Jump in. The water is fine.
There you go. Excellent. How old are you guys there, Carl? Are they varying ages? I guess adults, but we'd have young adults to fair to middle and 18 to 45. Okay. One of my favorite demographics. Yeah. Very well, awesome. That is awesome. So let's do a quick review for the apprenticeship class. What did you guys learn? The 16 of you, so I want 16 answers. What did you guys learn tonight that you're going to be able to use? What did you learn that you can use? That's the most important thing.
Unfortunately, I think a couple of them left already. I did see the names drop out on on
Okay.
who was there. So, but anyways,
Yeah.
if they're still here,
Yeah.
then go for it.
John learned he won a prize. Good. John's going to go far in this business, I can tell. John, there's a place for you at TACO. I can tell you right now. That's good. That's very good. All righty. Yeah, we have some guys left. That is correct. That is correct. Here's some advice, though. I mean, we've talked about this before. Some advice about training in general and whatever classes you take. All too often, we see this in the classes that we teach. A lot of guys are there just to get to the end.
Yeah.
They're not there to kind of experience, for the learning experience. They may have been told to be there or whatever, but they're there just to get to the end of the class and then get the hell out of there. And one of the things I've always recommended to people is take advantage of your learning. Especially if you're in an apprenticeship program. This is your career. This is your chosen career path. Take control of whatever training classes you go to. Always go, like if it's a class put on like the likes of us, always make a list. You're going to this class. Make a list of things specifically that you want to learn. What questions do you have for that instructor? Because we do like it when people come prepared. Go to your class prepared and ready to learn, as opposed to just being a passive viewer. Be an active participant. Take control of your learning. And if something doesn't make any sense, speak up. All right. If something sounds like complete and utter bullshit, speak up. And always ask questions. That way you're in control of what you're learning, and that's how you're going to really get good and have the most benefit. And then after you take your notes, study your notes, go over them, because that's how that stuff starts to stick. Oh, here's a good point from Doug. I've heard contractors complain about the cost of training people who might leave, but how much does it cost if you don't train them and they stay? That's right. That's right.
They would know that, right?
Yeah,
How
you
many
train
times-
people and they leave. Well, at least you're going to be dealing with competitors who know what they're doing, because who would you rather compete against? A guy who's just as good as you are, or an idiot? Because idiots are dangerous. I'll tell you what. Idiots are dangerous.
I scare me all the time.
Yeah. So yeah, I mean, my dad was one where he'd have guys that stayed with him for years and years, and then ultimately they left to start their own businesses. But what he didn't like it when they left. I'm not gonna kid you. He didn't like it when they left because this was he was making a lot of money off these guys. But he also understood that it was time for them to go on their own. And what he did was they talk about, a coaching tree, like you get one head coach and then all of his assistants go on to become head coaches and so on and so on. My dad had a plumbing tree, so to speak, where a lot of the guys who are doing business in that part of Massachusetts right now, and either directly or indirectly, can be traced back to my dad, who taught guys who taught them, and that's a mark to leave. I mean, that's a good thing.
Yeah, the good ones are let them go, let them do their thing, help them if they can to start their own businesses. And yes, you got to start over again and train a new guy. But it shouldn't be hard to find somebody new a lot of times. I know a lot of people turn around and say there's nobody good out there. They all suck, Well, on day one, they're not going to know all this stuff,
Right.
So that's why we do the training classes and we keep doing and keep going and keep going. So, there's always new people entering and they always need to be trained and learn what's happening. And I think our, over the years, the so to speak apprenticeship program kind of fizzled apart because everybody has gotten so busy and they just want to hire somebody that can just go from day one. And that's going to be hard. I mean, I remember when I started at TACO, there was no way I was going day one. And it took a while. It took a while to really learn.
Waiting.
Still waiting.
We're still waiting.
Good night, Jeff.
Yeah. Good night, Jeff. Carl said usually go to Wales Derby for training, but I can't do it, so you do this instead. Well, terrific. Excellent. And Jim De Palma wants me to ask you, Carl, who turned you on to TACO After Dark? I'm guessing it must have been Jim. I'm guessing. Didn't we have a nickname for Jim De Palma earlier? I forget what it was now.
Oh man.
What was our nickname for Mr. De Palma?
Oh yeah, and he was gone from the class at the time too.
Hmm. That's right. Yeah, Carl, Jim is your spiritual guru. Oh. And Jim, who do you call about any code question? I'm guessing it's Carl. He's got a little mutual society going on here. Oh, this is gonna bug me now because it was perfect. We had the
Oh, it
perfect
was
nickname
awesome.
for, yeah, perfect likeness for Jimmy. I can't now. Oh, that's gonna bother. We have to go back and listen to the recordings. That was the summer session, or was that this session?
The Knight.
The night?
He remembers. He was the Knight from yeah,
Holy Grail.
the Holy Grail. There it is.
Which night?
Wasn't it the French Knight on the roof?
Oh, yes.
So you were still there. That's right. He just didn't want to say it right away.
That's right, the night. Now go away or I shall taunt you a second time.
The knights that go knee.
Yeah, no, different nights. That's a different night. This is a
I
French
know.
night. That's Jimmy De Palma. Yeah, so go away or I shall taunt you a second time. Your mother was
forgot
a
all about
hamster
that.
and your father smelt of elderberries. Okay, here we go. It's
Yeah, okay.
it's devolving now. All right. You guys must love to listen to us do the monologue, I guess. All right. Doug makes a very good point. If you get someone new, you can train them in your way, right? Absolutely, the way you want them the way you want stuff done, you know. And if you're on your own business, you got to keep that pipeline full, you know. I talked to Bob Dudley out in your area, Rick. You know, he said to me he'll bring on like a half dozen apprentices a year, and maybe one of them lasts, but he knows because Bob's tough.
Oh yeah.
He'd be a tough guy to work for, very demanding, but very rewarding. You're gonna sink or you're gonna swim, and if you swim, then you've got a great job, and with tremendous opportunities. But yeah, he knows they're not going to last. He knows 5 of them aren't going to make it. That's just the process that he goes through.
Yeah.
You know, and as a result, he's got a pretty solid workforce too.
Yeah, but everybody's hungry. I mean, everybody's looking right now. If you ask most contractors, they're looking for help, and it's
Yeah,
not easy to find right now. So,
no, it's
No, it
definitely.
is not. No, it is not. I remember when I got volunteered to be on the education and training committee with AHRI a bunch of years ago, which has now been folded up. And the biggest concentration, I guess it was about 6, 7 years ago when I was there. And the biggest conversations that we were having was about workforce development, you know, and
Yep.
what do we do, and the statistics that they had. And what they had for statistics was the average age of the technician in the industry is 57. And
Wow.
this was already going back 5 years ago. And based on those days on want ads online, there was already a 10,000 job shortfall. So what they were figuring in the next 5 to 10 years, that 10,000 job shortfall was going to grow to about 40,000 based on everybody retiring and getting out of the industry. So,
Right.
and now it's even getting worse because more people are home. They're remodeling, they're doing work in their houses, they're moving their office to the house. So it's just going to get crazier. So yeah, I mean, I try to talk to as many young people as possible right now. Get into the industry now. You know,
Right.
because now is the time. Now is the time, as we all saw, who's essential, right? Plumbing and heating is essential,
Yeah.
and health workers. You know, grocery store and
Yeah, throw
garbage men
another.
too. But yeah,
Yeah. Well, throw another element in there. Also think about when did we have our the big building was late 80s into the 90s, right? That was a huge residential building boom in great parts of the country. Those homes, the mechanical systems in those homes are actually starting, they're due for upgrades and major work in the next few years. Somebody has to do that. That's again, that's one of those things what do they call good luck is when preparation meets opportunity, right? So the guy who's the contractor who's well positioned to take advantage of that opportunity, just understand the market you're in and where the houses were built and what kind of systems they have, and be prepared to be able to service and if not replace those specific types of systems. You're going to be well positioned to take advantage of that opportunity. Here I said 11 of your graduates went right into apprenticeship. That's excellent. That's excellent. After 13 graduated, 11 went into apprenticeship. That's terrific. That's terrific. It's a small number though, but in the big picture, Carl, isn't it a kind of a small number compared to what's needed?
Yeah. Yep. Especially in a heavy, in a heavy hydronics market where he is too, over in New Jersey and North Jersey. Yeah. So.
Very good.
Excellent. Glad to hear it.
Yeah. All right. Well, hey, listen, let's throw it. It's a nice part having the different companies under one roof. There you go. Some go to college. Absolutely. Yeah. All righty. Well, any more questions there, folks? If not, we may wrap this up early tonight. Only an hour and a half instead of one of our 2.5 hour night marathons.
I'm sure next week.
Everybody's probably a little tired. I don't know how late you guys stayed up last night, but maybe a little bit tired, and looks like we need another one tonight. So.
Yeah, I know. I've got the TV on in the background there, and it's just talking heads going on right now.
No politics.
No, but it's still going on. So
there you go. All right, very good.
That's all I was going with, so.
There you go. All right. Well, all right, then we're going to flip all the cards and say good night to everybody. Thank you all for joining us. We do appreciate you being here. And next week, we'll be looking forward to you.
Same bat time.
Same bat channel.
That's it. Good night,
all.